Hello students. So let us continue. Yesterday we discussed what is the Arrhenius theory is all about. What are the main points related to the Arrhenius theory that we discussed, right? So today we can go to the limitations of Arrhenius theory. No, Arrhenius theory cannot be uh, cannot be applied for both strong and weak electrolytes. So let us see what are the limitations one by one. First one, Arrhenius theory simply assumes the presence of ions in aqueous solution, and it does not explain such ionization, why such ionization can occur in water, which means no, yes, uh, Arrhenius theory is saying when electrolyte dissolves in water it just ionizes, or no, it produces ions when it dissolves in water. Why such ionization occurs, that no, he didn't had an answer. So why ionization occur when electrolyte dissolves in water? So let us talk about limitations. Limitations of Arrhenius theory. Arrhenius theory. Why ionization takes place for an electrolyte when it dissolves in water. When it dissolves in water. So how the ions are forming when it dissolves in water? There is no answer for that. That was one of the limitation. Then now, when this Arrhenius theory was applying for a weak electrolyte, it was okay. It was no just no obeying Arrhenius theory. But whenever we start applying for strong electrolyte, it doesn't work. Because especially we're talking about Ostwald dilution law. That what we discuss next. Now there now it's simply based on Arrhenius theory. So it is observed that Ostwald theory only applicable to weak electrolyte. When it's applying to a strong electrolyte, it doesn't work. So now the next point is Ostwald dilution law, which was based on Arrhenius theory. Ostwald Ostwald's dilution law, which was based on Arrhenius theory. Arrhenius theory do not work for strong electrolyte. Strong electrolyte. Which means no, yes, this is working for a weak electrolyte. When Arrhenius theory works, no, then Ostwald dilution law also work, because Ostwald dilution law simply based on the Arrhenius theory. So when Ostwald dilution law is applying, it found that no, it's applicable only to weak electrolyte, not for strong electrolyte. So that's the second no, limitation for you. Then Arrhenius theory takes into consideration the ionization of an electrolyte that takes place in presence of water. It does not consider the ionization that occur when electrolyte in the fused states, because now we know sodium chloride such electrolytes are already ionized in the fused state or in a solid state. When they are dissolved in water, they separate into free ions. This is what happening. But now, what is the ionization? What's the degree of ionization, or how whether they are ionized or not in the fused state or in the solid state? That cannot be explained by, that not considered by Arrhenius theory. But we observe that for a strong electrolyte like sodium chloride, potassium chloride, HCl, no, such electrolytes, no, not HCl, but some electrolytes are no, completely ionized even in the solid state as well. That suggests no, they are no, strong electrolytes, they are already ionized in the solid state. So next point, the ionization of strong electrolytes, ionization of strong electrolyte in the fused state, in the fused state is not considered. In the fused state is not considered. Next one, Arrhenius theory assumes the independent existence of ions but fails account for the factor which influence the mobility of the ion. So, such electrostatic and such as the electrostatic force of attraction, particularly at the uh, in a solution of moderate concentration. So there now, yes, we know electrolytes now exhibiting different mobility. We're talking about ionic mobility. Now, ion mobility of different ions have different mobility in a solution with respect to the concentration. Okay, that's one of the factor. Then also no, with the influence of a temperature and electrostatic force of attraction between the ions, everything influence the ionic mobility. So now if the electrostatic force of attraction is very high, which means no ions cannot able to move in the solution, which definitely affect the conductivity. Similarly, if the concentration is very dilute, we saw it's more now separated from each other, ionic conductivity is high. That means it's now affect the concentration as well. And the temperature, higher the temperature, that helps to break the force of attraction between the ions. So definitely this factor will influence. So no, so the point is what is the different ionic mobility of ions in different solution in different concentration, that's not considered in Arrhenius theory. So next point, ionic mobility of ions, ionic mobility of ions in different concentration. Ionic mobility of ions in different concentration now found to be different, sorry, 1 second. Found to be different by considering the electrostatic force of attraction, the electrostatic force of attraction between the ions. So the ionic mobility is different at different concentration. We talk about 1 molar solution, we talk about 2 molar solution, no, and 1 molar solution at different dilution. I will say no, the number of ions may be same, but at different concentration it found to be different. So why this ionic mobility is different in different concentration? That cannot be explained by Arrhenius theory. So next point, the degree of dissociation of a strong acid and weak base, strong acid and strong base were found to be decreased with increase in concentration. This is something now is something according to Arrhenius theory. This was the theory. The degree of ionization now found to be increased with the increase in dilution. That's something now he pointed out. But now, if the ions are less at less concentration, and if the ions are more at more dilution, means no, you have to get different results of acid base neutralization no reaction depending on the number of moles of ions. So it is found that no, always no, 1 mole of an acid combined with 1 mole of a base to get the corresponding salt and water. So what is the difference in what is the difference in now acid base neutralization? During we know during the acid base neutralization, heat will be released, heat energy will be released. So the amount of heat energy released at a low concentration and high concentration has to be different if no degree of ionization is different at different concentration. For a no for an acid base neutralization, we know heat energy will be released, so the amount of heat energy will be different for a for an acid at low concentration and at a high concentration. That has to be different because at low concentration the degree of ionization is different, high concentration the degree of ionization is also different. So that change should be shown in the heat of neutralization as well. But no, heat of neutralization found to be always same whether no when you're talking about 1 mole of an acid combined with the 1 mole of a base to get the products. So why there is no real variation? Because no, the degree of ionization always varies with the concentration. So why such effects doesn't see, especially in a strong acid strong base titration. The heat of neutralization, heat of neutralization for a strong acid and strong base. Heat of neutralization of a strong acid and strong base doesn't vary with the concentration. So that's the next point. Now, next point, the theory could not explain the variation. Could not explain the variation of transport number of ion with the concentration. Variation of transport number. Variation of transport number with concentration. Variation of transport number with concentration cannot be explained. Cannot be explained. So what I mean by transport number, that we will know, we will discuss more about transport number in the later session. So just for the time you understand, transport number means it is the fraction of current. It is the fraction of currents carried by a particular ion. A particular ion in a solution. In a solution, that we will call transport number. What is the amount of current carried by a particular ion? Because no, the transport number found to be different for a for a same electrolyte at different concentration. It's found to be different. So why transport number varies? The variation of transport number with respect to concentration cannot be explained, because no, transport number always depends on ionic mobility. If force of attraction is higher, no, ions cannot able to move as freely as they do in the dilute solution. So always no, if ions can able to move faster, yes, no, transport number will be higher as well. So definitely transport number varies with the concentration. So why it's vary, that cannot be explained by Arrhenius theory. So these are the limitations of Arrhenius theory. So let us now discuss once again. First one, no, Arrhenius theory assumes the presence of ions in a solution. Why that ions are forming? Why that ions are forming in a solution? That cannot be explained by Arrhenius theory. Second point, Ostwald dilution law. which we'll discuss later. As next point, Ostwald dilution theory cannot be applicable to a strong electrolyte. It applies for a weak electrolytes only. So now that means Ostwald dilution law doesn't work for a strong electrolyte. So why it's so? That cannot be explained by Arrhenius theory. So next one, yeah, in the fused state, now for a strong electrolytes are already ionized in the fused state, or no, in the solid state you can imagine. So no, the ionization of such electrolytes in the fused state do not consider. That was another negative point. Then Arrhenius theory assumes the independent existence of ions. Uh, and also which influence the mobility. Yeah, mobility of an ion is different at different concentration. No, why ionic mobility varies with different concentration? Because ionic mobility definitely varies with the electrostatic force of attraction. If the electrostatic force of attraction between the ions is higher, ion cannot able to move as freely as they do in the dilute solution. So that is not considered. Then the degree of ionization. No, it is found to be decrease with the increase in concentration, or no degree of ionization increase with the increase in dilution. So no, that change you may expect in acid base neutralization reaction, because no, if more number of ions are forming, no, one mole of a H plus ion can combine with one mole of a OH minus ion to form the corresponding neutral water. So we're talking about acid base neutralization, sorry, heat of enthalpy of neutralization means the amount of heat released when an acid and base are neutralized. So that has to be different at different concentration, but no, it's not found. So when one mole of an acid is taken, irrespective of the concentration, it always neutralizes with one mole of a base. So that also doesn't work. Finally, no, theory does not explain for a variation of transport number. Why transport number varies at different concentration? Transport number means the amount of current, the fraction of current carried by a particular ion in a solution. That we can call what's transport number. So variation of transport number in a solution also cannot be explained. So these are the limitations of Arrhenius theory. Now let us go to the Ostwald dilution law. Ostwald dilution law. Ostwald's dilution law. Now Ostwald dilution law. Now imagining that partial ionization is taking place in a moderate concentration, then once it is ionized, one electrolyte dissolves in water, it achieves an equilibrium, and using that equilibrium state you can find the concentration, sorry, equilibrium constant, or now we can say dissociation constant of a weak electrolyte in a solution can be determined. So now Oswald dilution law, let us imagine how they dissociate. For example, Ba is an electrolyte which dissociate into B plus and A minus. No, which means they are in equilibrium. So this is something now assumes in Arrhenius theory as well as in the Oswald dilution theory. When a weak electrolyte, or it doesn't really put that a weak electrolyte behaves differently and the strong electrolyte behave differently. That was the main problem. So when according to Oswald dilution law, when an electrolyte dissolves in water, they ionizes to corresponding cation and anion, and they exist an equilibrium. There is an equilibrium between the ions and unionized molecule. So if there is an equilibrium between the unionized molecule and ions, no, you can find the equilibrium constant. Something now we can apply law of law of equilibrium to find the equilibrium constant. So first one, no, they ionizes in aqueous solution, and there is an equilibrium exists between a unionized molecule and ionized and ions. So this is something now we studies in equilibrium as well. At equilibrium, the rate of forward reaction will be equal to rate of backward reaction, and there is a dynamic equilibrium existing between the two species. We're talking about unionized molecule and ions. So this is what now we're talking about chemical equilibrium, where now they are always in dynamic equilibrium, which means now both forward and backward reaction is taking place, but at the same rate. So it's just not like nothing is happening, it's happening at both direction but at equal rate. So that's the problem. So that one we will call it's a dynamic equilibrium. Now using the by applying Arrhenius theory as well as in Ostwald dilution law, you can find the degree of dissociation as well. So let us let us calculate how it can be found. Imagine at initial concentration, at initial condition or initial concentration, let C be the concentration of electrolyte, and at initial condition means no, it's doesn't really ionized. So initial condition means no, what's the amount of electrolyte that you've taken. So initial concentration, let it be C. At now let 0 be the concentration of ion at initial condition, at initial concentration. Now after achieving equilibrium, at equilibrium stage, now let express the concentration of the ions in terms of alpha, where alpha is the degree of ionization or degree of dissociation. So if now 1 mole of ions are forming, cation and anions are forming, then both concentration will be equal. So let it be C alpha, where C is the initial concentration, alpha is the degree of ionization. So we express the concentration of ions at equilibrium in terms of alpha. So initial concentration into degree of dissociation will give you the concentration of a particular ions at equilibrium. So C alpha is nothing but concentration at equilibrium, the concentration of ions at equilibrium. So we have which means C alpha is start producing, means you can see a C alpha concentration will be decreased from the electrolyte. That means now we talking about reactants and product. C alpha concentration will be decreased from here, from the reactant, and C alpha concentration of product start forming. So C minus C alpha will be the concentration of electrolyte that we taken Va at equilibrium. C alpha will be the concentration of ions at equilibrium. So let us now we have the concentration of ions and concentration of the electrolyte at equilibrium. Now by applying law of equilibrium, you can find the dissociation constant or equilibrium constant. K is equal to product of concentration of products, that is here C alpha. So C alpha into C alpha. These are the ions that is formed. So you multiply the concentration of both the ions C alpha into C alpha divided by C minus C alpha, concentration of the reactant over here electrolyte. So C alpha divided by C minus C alpha. Let us take C outside, so you will get C alpha into C alpha divided by C into 1 minus alpha, which will give you C cancels. So net effect will be C alpha square divided by 1 minus alpha. This is the equation for dissociation constant or equilibrium constant of an electrolyte. So if we have alpha, that is degree of dissociation, if we have initial concentration, then you can find the equilibrium constant or dissociation constant that you can imagine. Okay, so having this equation, you can Now you imagine if 1 mole of a if 1 mole of an electrolyte is taken, 1 mole of an electrolyte is taken in a V volume of the solution. Let it be no V is the volume of the solution. Then you can apply now in terms of C. Let it be C equal to 1 by V, where C is the 1 mole of an electrolyte that is taken. So let us apply K is equal to in terms of C alpha square divided by 1 minus alpha. C alpha square divided by 1 minus alpha. This time I put C is equal to 1 by V. So it will be 1 by V alpha square divided by 1 minus alpha. This is the dissociation constant in terms of volume. Okay, so we have two expressions. C alpha K is equal to C alpha square divided by 1 minus alpha, then K is equal to alpha square by V into 1 minus alpha. Now imagine alpha is actually very small compared to 1, because the degree of dissociation, especially for a weak electrolyte, that is very small. So that way you can simply negotiate the value of alpha at the denominator, because 1 is very much greater than alpha. If you apply that, you will get K is equal to C alpha square, and here K is equal to, or another expression, K is equal to alpha square divided by V. Okay, so now let us have an expression for alpha. Alpha square is equal to K by C, or alpha is equal to root K by C. Here alpha K is equal to alpha square divided by V, alpha square is equal to KV, and alpha is equal to root KV. So we get into expression for degree of dissociation. So degree of dissociation inversely proportional to concentration, especially for a weak electrolyte. Degree of dissociation directly proportional to volume. Higher the volume, higher the degree of dissociation. So this what Ostwald dilution law. How the degree of dissociation and concentration are related for a electrolyte. How the degree of dissociation and volume is related with respect to volume. So these are the two relationship that brings by Ostwald dilution's law. So it assumed that both it can be applied for both strong and weak electrolyte, but it's found that this theory, these equations and everything is works only for a weak electrolyte. For strong electrolyte, it doesn't works. So which means Ostwald dilution law is perfectly okay for a weak electrolyte, not for a strong electrolyte. So we talk about Ostwald limitations of Ostwald dilution law. You can simply say that Ostwald dilution law works for a weak electrolyte, not for a strong electrolyte. So what's what actually he brings? He brings what is the relationship between the degree of dissociation and the concentration of electrolyte? What is the relationship between the degree of dissociation and the volume of an electrolyte? If you have both two, you can find it. So it brings K is nothing but equilibrium constant or dissociation constant. That also you have to keep in mind. So you need this data to find a corresponding values. If you want alpha, if you K and C are provided, you can find alpha. So three terms are there which you can connect. So next point is related to what are the applications. What are the applications of Ostwald dilution law? First one, you can calculate the degree of ionization of weak acid and weak. Applications. Applications of Ostwald dilution law. Ostwald's dilution law. Now, Ostwald dilution law, first application, you can find the degree of dissociation of degree of ionization of weak acids and weak base. The degree of dissociation, that is alpha. We can find the alpha degree of dissociation of weak acids and weak base. So same equation, same way you can derive, if talking about weak acids, no, we represent K as Ka, where Ka represent acid dissociation constant or acid ionization constant. Acid ionization constant. And Kb will be the no base dissociation constant, base ionization constant. So now you simply apply here. No, instead of K it will be no Ka. That's only change. Okay. So the equation you can modify. Ka is equal to C alpha square divided by 1 minus alpha. And we know alpha is greater, alpha is very much less than 1, so we simply neglect it. So Ka is equal to C alpha square, and alpha square is equal to Ka divided by C, and alpha will be equal to root Ka divided by C. So that's an equation you can imagine for a weak acids, the degree of dissociation and the dissociation acid dissociation constant with respect to concentration, how it is related. This is the way it is related. Similarly, for a weak base, now you can apply alpha is equal to root of Kb divided by C. So this is the equation you can remember. You can find degree of dissociation if Ka and Kb and concentration are provided. So that is a first application. Second application. How this no? You can find the pH of the aqueous solution of weak acids and weak base. pH is nothing but no negative logarithm of concentration of hydronium ion or H plus ion, you can imagine. So now if for example where acid Ha acid ionizes in water to produce hydronium ion and no hydronium ion and OH minus, sorry, A minus will be no will be produced, which is in equilibrium, especially for a weak acid. So here now you find the dissociation constant as Ka, which is equal to this, let it be C alpha at equilibrium, and C into C minus C alpha will be the concentration of Ha acid now at equilibrium. Remember, at equilibrium. So now the concentration of water we taken as unity. So Ka will be equal to no C alpha into C alpha divided by C into C minus alpha. So C alpha is nothing but the concentration of hydronium ion. So if you have the value C alpha, you can find pH as well. So pH will be equal to minus log C alpha. That's the way you can find the pH of the solution. We know pH plus POH will be equal to 14. So instead of no instead of Ka, you imagine Kb, no for a weak base, how it will change, because no if we have no if it is a base instead of an acid, if it is a base, it will be, sorry, it will be no OH minus. So it will be B minus plus no. Here now B minus, and you can simply imagine ionization, not water that much influencing. So you can write HB at equilibrium B is B minus and OH minus. So let it be C minus C alpha, and C alpha will be the concentration for a weak base. Now if you have no C alpha, that will be give you the concentration of hydroxide ion. So instead of pH, you are actually getting POH for a weak base. So once you got no POH, which will be equal to minus log C alpha, you can still find pH by now 14 minus POH. 14 minus POH will be give you the pH of a weak base, because now from a weak base we are going to get the POH first. After getting POH you can find pH by 14 minus pH. Sorry, 14 minus POH will give you pH. And finally the ionization constants of weak acids and weak base. Now imagine, now if calculation of ionization constant of weak acid and weak base. Now imagine if alpha you have, that you can find by lambda m divided by lambda m 0. That's something we using applying Kohlrausch's law. If now imagine if lambda m and lambda 0 is m is given, which is actually nothing but degree of dissociation. So if alpha value we have now, that you can still obtain by this equation lambda m by lambda 0 m, because now we found another equation alpha, say Ka is equal to C alpha square for a weak acid, or K is equal to C alpha square. So there now alpha and C need to be provided. So here now if lambda m and lambda 0 m is given, how can you find alpha? Still you can find lambda m by lambda 0 m will give you K, sorry, lambda m by lambda 0 m will give you alpha. Once you have alpha you can find Ka is equal to C alpha square, Kp will be equal to C alpha square. Using this equation you can find the acid dissociation constant, base dissociation constant. So this is the way you can know. Once you got alpha, once you have now this C, you can still find the acid dissociation constant as well as base dissociation constant. So these are the important applications of Ostwald dilution flow. Please go through the textbook. No, it's very important. You have to continuously read to keep these things in your mind. Okay. Thanks for listening. Let us wind up.